Now that we learned about sensitivity, specificity, prevalence, and the positive and negative predictive values, we want to apply those problems to a very interesting situation that actually happens quite a bit in screening tests. For example, drug screening tests, medical screening tests, that kind of thing. So we're going to suppose that drug use amongst air traffic controllers in the US has a prevalence rate of 0.7%. It's extremely small, less than a single percent. Right? And further suppose that the FAA is using a drug screening test that has a 96% sensitivity and 93% specificity. Okay, so we're going to look at a sample of 1,000 air traffic controllers. We're going to fill in this table. All right, well, let's think here. We know that this particular test has a 96% sensitivity and 93% specificity, so that's great. That's how we're going to help figure out our test rates here. What's really interesting to me is our prevalence rate. Write that right there. We know that we have somehow magically know. Of course, real life, we don't get to know things like this as precisely as this, but we'll pretend that we know that the prevalence rate of drug use amongst air traffic controllers is 0.7. But we're polling 1,000 of them, or we're sampling 1,000 of them. It's probably not a poll, it's probably a drug test. All right, so we need to take 0.7% and multiply it by 1,000. But 0.7% is 0.007. So I'm going to take 0.007, I'm going to multiply it by 1,000. And that gets me 7. So out of 1,000 air traffic controllers, I expect 7 of them to have drug use. And then I expect 993 of them to not use drugs, which is good, right? We don't want our air traffic controllers, hopefully, using drugs that could be dangerous for all involved. Okay, so now remember that the test had a 96% sensitivity. Now, sensitivity, let's go back here and look at it. Sensitivity is the true positive rate, right? So it's A divided by A plus C. Okay, well, I already know what A plus C is. A plus C is 7. It's right here, right? I mean, if it makes you happy, you can write it that way. A plus C is going to be 7. So the sensitivity is getting me this cell right here, right? That's where the sensitivity is going to come in. Here, let me highlight it. Let me pick a color. Something that both of them have. How about this? Okay, so that sensitivity is going to get me that cell right there, the true positive rate. So I'm going to take 7, I'm going to multiply it by the 0.96. And here I'm going to multiply this just so you guys can see this. This is 0.007 times 1,000. That's where that came from. I don't think the A plus C is as important. So this is 7 right here. All right, so if I take 7 and I multiply it by 0.96, I'm going to get 6.72. There we go. It's a decimal, I know, but you know, these are rates over a large population, so you're not going to have everything work out to be whole numbers. Don't round it. Leave the 0.72. That's important. Okay, well, let's think about this. If the whole column adds up to 7, and this cell right here, the green cell, is 6.72, doesn't this one have to be 0.28? Right? That way, the two of them will make 7. Right? 6.72 plus 0.28 makes 7. All right, now what about the specificity? The specificity is the true negative rate. So let me go, how about, I don't want to do red, let's do blue. All right, so the true negative rate will be this cell down here. Oop, not there, here. There we have it. Okay, so I'm going to take 0.993, excuse me, 0.93, there we go. I'm going to multiply it by 993. I'm going to get 923.49 right here. So 993 times 93% gets me my true negative rate right there. Okay, well then I know that the whole column makes 993. So if I take 993 and I subtract away 923.49, I'm going to have the difference, which is 69.51. And if you don't believe me, 0.93 times 993 makes that. Take 993, take away that number. There you have it. Okay, so there's that. Now to get these totals over here, I need to add up the row because this is the row total. So I need to take 69.51, I need to add to it 6.72. Okay, well that will get me 76.23. Down here I'm going to have 923.77 because 0.28 only adds a little bit more onto this 923 over here. So that gets me that total. So I have found all my totals right here. Actually, I think I'm going to not underline everything. I'll just underline the ones that we had to calculate. So I used the rate right there, the prevalence rate to find this cell. Oops. There. So the prevalence rate found me this cell. The sensitivity then found me this portion. And then I used the fact that there was 1,000 to find this, 993, and then I used the blue portion, the 93%, to find this cell right here. Now, here comes the fun part. If an air traffic controller tests positive, well, that'd be this row right here. If they test positive, what is the probability that they actually are a drug user? They tested positive for drugs. What are the chances that they truly are a positive? Well, let me type that up. Well, according to what we learned about the conditional probability, what they're asking us is, given that they tested positive, what's the chances they are a drug user? That's the number of ways that you can both test positive and be a drug user, which would be 6.72, divided by the number of ways you can test positive, which is actually 76.23. So if you take 6.72 and you divide it by 76.23, you would have, I don't think you're going to believe me when I do this, so I will actually do it right here. Oops. 6.72 divided by 76.23. I typed too fast. 0.088. Did you catch that? Because that's very small. You tested positive, but the chances of you actually being a drug user is less than 10%, which is very, very low. All right, now what if the prevalence rate wasn't so low? What if it's 15%, which would be very, very bad, right? If 15% of air traffic controllers are drug users, but bear with me. If the prevalence rate was 15%, that would change how we calculate this cell right here, because then we would take 15% of 1,000, which is 150, 0.15 times 150, or times 1,000, excuse me, is 150. Okay, well now I still find my sensitivity the same way as I did before. I take 0.96, which is my sensitivity, and I multiply it by my total, which is 150. So 0.96 times 150 gets me 144. So this number right here becomes 144, and this number is 6. This, okay, well there's 850 total left over here. And then my specificity rate is going to get me this cell right here. So I take 850 and I multiply it by my sensitivity, my specificity. Sensitivity is the green, specificity is the blue. All right, whoop, there it is. So I'm going to take 0.93 and I'm going to multiply it by 850. And I get 790.5. Okay. That means that this number is 59.5 because together they've got to make 850. This is 796.5 and this is 203.5. I'm just adding these two numbers up and adding these two numbers up. And notice if you do it right, they should all make 1,000 for the rows and the two columns should make 1,000. Now, what is the prevalence of, or the probability of being a drug user given that you tested positive? All right, so it's the same calculation as before, it's just that the numbers have changed. So now instead of 6.72 divided by 76.23, it's now 144 divided by 203.5. And this is really revealing something very, very important about medical testing and also things like um, uh, TSA screenings, trying to find a terrorist at an airport. It's a very rare event. And rare events, screening tests for those rare events will always have this kind of problem that we have in Part B right here. Okay, so what we're seeing here is that when something is rare, like this example up here, what was happening was the 6.72, which are the true positives, are getting countermanded or outnumbered, if you will, by all these false ones, right? So these people are not drug users, but they're testing positive, right? That means that our positive predictive rate, which I should have called it that, sorry, that's what we found here. That positive predictive rate is very low because the 6.72, which are the true positives, are getting swallowed up by this number over here and this total, right? The total is so large because this is so large, right? And that's what I wrote down here, right? Screening tests for rare things like rare diseases or terrorists at the airport. There's not going to be, 80,000 of them. There's going to be like one or two. Finding something that's rare like that, finding a needle in a haystack literally, is going to be very tricky to do. And you're always going to have positive problems with your positive predictive rate. I'm just going to write needle in a haystack, which is an American idiom for finding something very tiny and something very large, right? So you're always going to have this problem with a very um, weird positive predictive rate being very low, right? Because the false positives, that was cell B, that's this cell over here on the right, outnumber the true positives, that green cell. It didn't happen for something that's not rare, right? That's why I stress the rare thing. Because when it's not rare, like letter C, it was no problem. But when it is rare, like letter B, there's a big problem. And that means that we have to be very careful about the decisions we make, right? Whether it be in drug testing or airport testing for terrorism, or the counseling we make for patients after we've told them that they've tested positive for a disease. If it's something that's very rare, we have to be very cautious about what we're telling people because it's very possible that even though they tested positive for that rare disease, they don't actually have it. That's one of the issues with screening tests as opposed to a diagnostic test. So that's something you can learn about in medical professions if you go on. All right, so hopefully we've learned something very cautionary about positive results on things that are rare. If it is a rare item, the positive result might not mean what you think it means. I mean, normally you think, oh, sensitivity, specificity, they're in the 90s. This should be a great test. But if your prevalence rate is really small, then even though those percentages are high, your positive predictive rate, which is kind of an important thing, the chance of you really having this, given that you tested positive, is less than 10%. Really small. And that's something to think about when not only do you receive positive tests from something or you give positive tests to a patient or a client or something like that.